Today we have Professor Noah Goodman. He's from Stanford University. He's associate professor there. He is running the computation and cognition lab there at Stanford. His research interests include the computational basis for natural and artificial languages and intelligence, as well as merging behavioral experiments along with the formal methods of statistics and computer programming. So he had his PhD he received from the University of Austin in Texas. And he did his postdoc at MIT, where he worked as a research scientist. And finally he has over 150 papers published across mathematics, computer science, psychology, linguistics. So he's here to talk to us today about probabilistic languages. Thank you.
Hi, so I'm super happy to be here today. I feel like, given that I run the computation and cognition lab, going and talking to cognitive computing enthusiasts is a perfect fit. The work that I do is at the intersection between understanding human cognition and developing principles and systems for artificial intelligence. And you're going to see that throughout the talk. I'm going to sort of bias it on the side of trying to build models to explain human cognition, because I think that's probably the most unique and fun thing for a crowd like this. And so let me start with what's really kind of a underlying philosophical question in cognitive science, which is, what is knowledge? So there's a lot of different kinds of knowledge. There's knowledge like this, where you have encyclopedic knowledge of the capitals of states. Austin is the capital of Texas, and so on. But there's also knowledge like this. You can imagine I'm holding a hammer and I toss it, and you can imagine the trajectory, the arc through the air, the way that it spins, what might happen to a window when it hits it. And so there's some kind of knowledge about the world implicit in that as well, knowledge about physics and materials. Or in a social domain, you can imagine you call your best friend on the phone and he immediately screams at you and hangs up the phone. And you're left wondering, why did he do that? And you're not at a complete loss. You can manufacture explanations. Things like, maybe he wanted to hurt your feelings, maybe he thought you were a telemarketer, maybe he had a really bad day. And so the knowledge that we have about how people behave and why is another kind of knowledge, which isn't encyclopedic, but it's somehow a richer, implicit kind of knowledge. So when we think about knowledge, we have to answer questions like, what is it that we actually know about the world? What are these kinds of things? How can we use that knowledge for thinking and reasoning and planning? And finally, where does the knowledge come from? How's it learned? So what I want to do in the next couple of minutes is give you guys an idea of one approach to knowledge and representing knowledge. And it's going to start in something that people don't usually think of as knowledge, but it is, which is computer programs. So computer programs are knowledge of what to do, right? They're very explicit instructions that we can give to a machine to tell it exactly how to do something. So for instance, here's the simplest program, almost. 1 plus 2 plus 3 plus 4 tells the computer, add up these integers and give me the answer, 10, something like that. We can, of course, also write that in a slightly more abstracted way. We can write a function. I'll use JavaScript throughout this talk. We can write a function, sum, that takes in 4 numbers and says, okay, what I do is return those 4 numbers, fine. And then we can compute the same thing by applying the sum to 1, 2, 3, 4. Or we could be even a little bit more abstract. We can write a function that takes in an arbitrary number of numbers and recursively adds them together until there are no more numbers. And the point of writing these 3 things is that each of these is a representation telling the machine what to do. But critically, they have different levels of abstraction. So computer programs are powerful because you can build very abstract representations of how to do something, or what to do. Things like the recursive function, or higher order functions, or great things like that. Okay, so it turns out, and this is well known, that computer programs are universal for representing a certain kind of knowledge, deterministic how-to knowledge. On the other hand, they're not so good at representing another kind of knowledge, which is uncertain knowledge. So when I talk about uncertainty, there's a number of senses of uncertainty. One is something like noisy input. So you're driving down the highway and it's raining and so you can't quite make out the street sign. But you don't just explode or say that's a failure of my rule system and drive off the side of the highway. You deal gracefully with that uncertainty due to noisy input. More interestingly, uncertainty comes in the form of a lack of information, an under-constrained inference problem. So if we go back to your friend who's yelling at you on the phone, the basic question here is, why did your friend yell at you? You're coming up with answers like, maybe he wanted to hurt you, maybe he thought you were a telemarketer, and you're doing it on the basis of some knowledge that says, look, I only observe the action, but I know how beliefs and desires are related to actions, and so I can make a pretty good guess. We have an under-constrained inference problem that we have to solve here. Given the action, what are the beliefs, what are the desires, and so on. Just one more example of uncertainty is the hammer flying through the air, right? We don't know exactly how it's going to fly through the air. We don't know exactly where it's going to hit the window or what it's going to do to the window, but we have some pretty good guesses. So there's some uncertainty, which is not just complete ignorance, it's knowledge with some statistical uncertainty built in. Okay, so the basic question then is, how can we start with this beautiful representation of knowledge that we have in computer programs and turn it into something that can represent uncertain knowledge, that can actually capture this uncertainty? It turns out that there's actually a very simple approach to this, well, initially very simple, which is to say, I'm just going to take my programming language, my deterministic programming language, and I'm going to add a random operator. In this case, I'm calling it flip, so something that flips a coin with a given probability. And otherwise, it's the same programming language as before. So imagine you take JavaScript and you add this flip operator, flips a coin, it might come out heads one time, tails another time, heads again, and then you add them up and you get 2. And the critical thing here, this is not particularly surprising or mysterious, but the critical thing here is that, of course, if I do this over and over again, I'm going to get different answers. I might get 0, I might get 1. And then you could imagine making the histogram of return values that you get from running this over and over. And it's going to look something like this. So what you have over here is a probability distribution. It's this probability distribution. And what you have over here is a random, or what we call a probabilistic program. And it turns out that these two things are equivalent to each other. So the sampling semantics for describing a probability distribution and the usual mathematical semantics for describing a probability distribution are actually equivalent in the sense that any computable probability distribution can be represented by some random program like this. It's a probabilistic version of the Church-Turing thesis. What else do you think of that? Okay, so I'm going to show you a bunch of much more interesting probabilistic programs and applications, but there's one more ingredient. So far what we can do is basically we've added, rand to JavaScript, which was already there. The critical thing is that we're not going to just forward sample and say, oh, look, there's a distribution that we get if we look at the histogram. We're also going to have an operator for doing conditional inference. So syntactically, it looks like this. You take the infer function and you pass it a function with no arguments. Inside of it, you give some, think of this as the model that you have of the world, the knowledge, the value you're interested in, the return value. But critically, you can also provide conditions. So this says, hey, I know that A, B, and C are random flips that come up heads 30% of the time. I want to know what A plus B plus C is, assuming that A plus B turns out to be 1. So to give you some intuition for how to think about that, we can actually, one potential way of defining the infer operator is to do exactly the same thing we were doing before. So we run this program, we sample random values. The return value here is 2, but critically we're also evaluating what's inside the condition. So in this case, A plus B is 1, that's equal to 1, so that's true. And what we do is we keep doing this, and anytime the condition is false, anytime any conditions are false, we throw that sample out. So keep doing this, throw out the samples, the executions where the condition is false, make a histogram at the end of the day. And it turns out that what you get from this is called rejection sampling, is the conditional distribution given the condition. So it's some other distribution that is a sort of hypothetical inference of what must have been true given that the condition is true. By the way, there's a thing that I like here. This is, it occurred to me at some point, very similar to what Sherlock Holmes says. It is an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. And then we add up the truth, and that's the only difference. So for those of you who are familiar with probability and statistics, this is equivalent to the standard definition of conditional probability, the Kolmogorov definition. But it's much more intuitive from a computational perspective. Okay, so here's the basic idea. Probabilistic programs, we start with a programming language that gives us a universal representation for deterministic knowledge, what to do, and we repurpose it by adding random primitives in order to represent uncertain knowledge, and then we use it to describe basically what the world does. So I imagine that the execution of this program with its random choices and uncertainty corresponds to how the world works and how the world gives rise to the values that I can actually observe. So that's the basic computational structure of a programming language with random operators. And then by adding the infer operator, inference, we can use that for hypothetical reasoning. So I do want to make a big caveat here so that nobody thinks I'm being naive, which is that the specification of infer in terms of rejection sampling is mathematically correct, but it's extremely inefficient for most uses that we're going to want to put it to. So we don't actually implement it that way most of the time. There are many equivalent or approximate implementations of the same thing, things like Markov chain Monte Carlo, sequential Monte Carlo, variational inference, and so on. Okay, so the language that I'm showing you all of this in, I thought I should tell you, is called WebPeople, Web PPL. You can go play around with it. It's at webpeople.org. And it's basically JavaScript minus a little bit of mutation, but plus all of the stuff for doing probabilistic programming, random choices and inference. Okay. That was your 10-minute crash course introduction to what is a probabilistic program. And at this point, you're probably sitting there thinking, either that's really simple, it looks kind of boring, I can't imagine doing anything with that, or wow, that's really complicated and cool, I can't imagine doing anything with that. So let me spend the rest of the talk showing you how to do something with probabilistic programming languages. And the basic goal here is to sort of progressively build up more and more interesting aspects of human cognition modeled by writing probabilistic programs. Okay, everybody with me? Ish? Yeah. This is where you nod. Okay, great, thanks. By the way, I should say you should feel free to ask questions in the middle if you have them. Raise your hand and I'll notice you eventually. I don't mind stopping to explain. Okay, so let's start with a thought experiment. And this thought experiment is intended to be kind of naive. I want to imagine, think about tug of war. Tug of war is great because it's a team game that almost everybody has played and everybody knows what it is. And then we're going to do a little exercise. We're just going to think about the concepts that come to mind when you think about tug of war. And then we're going to see whether we can capture those concepts with a probabilistic program. Okay, so of course I pre-canned the thinking about concepts. I think about tug of war. And the first thing that comes to mind is the strength of a player. But the strength isn't all that's there. There's also laziness, because a player doesn't always pull with their whole strength on any given match. That only matters, strength and laziness, because there's pulling, right? They use their brawn to pull on the rope. In tug of war, there are teams. And critically, the whole point of this is that of the two teams, there's going to be a winner. Okay, that's the set of sort of words that I want to try to capture. Now what we're going to do is we're going to write a set of probabilistic program function definitions that capture some version of those in the simplest way that we can imagine. Simplest way I can imagine. So first is strength, and we say, look, strength is really just a function that is a property of a person. So it's a function that takes a person and returns a random value, which is drawn from a Gaussian normal distribution, so some real number which is their random strength. I won't go into it in much detail here, but what this mem says is that every time you apply this function to the same person, you should get the same answer, it's memo-wise, and that's in order to have somebody's strength be persistent over time. In contrast, laziness is another function that takes a person and gives back a random answer. In this case, you flip a coin and decide whether they're lazy or not. And it's not memoized because that we want that to be able to vary from one match to another.
And just one little thing about the memorization one, but because strength is one of those things that the more times you use it, the stronger you get. So it actually should be adding some increment every time you use it.
So we're ignoring that.
Okay.
You can imagine, the great thing about probabilistic programming is that it's a specification language for writing down the knowledge you have about a domain. You can imagine doing that, right? Okay, now I'm going to make this a fancier function that captures how strength changes and such, but I'm not going to. I'm going to make this as simple as I can. Is there another question?
Do you allow negative values for strength?
In this model that I'm writing down, yes, because I wanted it to be simple. I could, of course, instead of using Gaussian, have done something like, Gaussian squared, which will always be positive or something like this. Also, the thing about this model is that strength only matters with respect to other people, and there's no absolute strength. And so it doesn't actually matter where 0 is, it's just who's stronger than who.
Is this only available in JavaScript, no other language?
So web people is only available in JavaScript. There are some other probabilistic programming languages that are in a smattering of other languages. I can tell you more about that later on. By the way, you might be wondering why JavaScript. The answer is that of all of the dynamic languages, because I wanted to be using a dynamic language, JavaScript is by far the most portable, because I like to use this for teaching and not have to get all of the students to install the thing, which takes days. And also has the best compilers. We used to use Lisp and Scheme, but the compilers are terrible and usually unsupported. And so, anyway, that's a whole other thing to talk about. But let's go back to tug of war. Okay, so we've got strength, we've got laziness. Pulling, this is the simplest thing I could think to write down for pulling. We say, okay, it's a function that takes the person, checks whether they're lazy. If they're lazy, then they pull with half of their strength, and if they're not lazy, they pull with their whole strength. Okay? Each person on the team is pulling. So we map the pulling function over team, apply pulling to each person on the team, and then take the sum of how hard each of those people is pulling. Remember, that's a random thing, so how hard they're pulling on this particular execution that we're looking at. And then we say, okay, and there's the winner, well, I called it beat, so team 1 beats team 2 if the total pulling of team 1 is greater than the total pulling of team 2. So the team that pulls hardest wins. Okay, so you should be thinking, yeah, but that's so simple. But now I'm going to show you that this is actually not as simple as you thought. So what can we do with this set of stochastic functions, this set of probabilistic functions? Well, we can do inferences like this one. So this is an inference where we provide some evidence, some observations. So we observe that Bob and Mary beat Tom and Sue, and that Bob and Bev beat Jane and Jim. And then we ask, okay, so how strong is Bob? And you can imagine. So imagine that to yourself. And now just to get you kind of moving in the right direction, imagine a different set of observations where Bob and Mary beat Tom and Sue, and then Bob and Mary again beat Jane and Jim. And then the question is, does your estimate of Bob's strength go down from that evidence or up? How many people say down? How many people say up? Yeah. Okay. Most people didn't say anything. Well, think about it. Here's the catch. I can actually do that experiment because I'm a psychologist. So we get a whole bunch of people, in this case 15 or 30 or something like that. We show them little tournaments of either singles or doubles, and on each match we show them which team wins. And then we choose one of the players and we say, okay, so how strong is that player? And we get human ratings of strength. And then what we can do is look at the average human strength rating from each condition and compare it to the model's predictions, the expected strength according to the model from the same evidence. And here are the results. So I'm showing you the human data on the x-axis and the model predictions on the y-axis. And the correlation between the two is around 0.99. So we're explaining basically all of the variance in people's judgments about this data. And it's not just because their judgments are noise. It's very systematic, right? There's nice gradation and systematicity between the conditions. So there's something in this simple model that is explaining how people look at this evidence and aggregate it and might discount spurious evidence or confounded evidence in order to come up with an estimate of strength. By the way, there's a fun fact about this, which is that the singles tournament version of this model, so even simpler than the one that I showed you, is equivalent to the model that Microsoft calls TrueSkill that they published in NIPS maybe 5 or 10 years ago. And it's the model that's actually deployed for matching players in Xbox Live. So they use it for estimating the strength of the skill of players and then matching up players of similar skill. They made a big deal out of it because it was a much better model than the previous model, which had been used for chess ratings before that. So that's kind of an interesting case where a very simple probabilistic program turns out to give something that's actually a state-of-the-art, interesting, useful model. And ours goes to multiple player teams as well. Yeah.
So I guess if your system had done something like, say, a person's strength is defined as like a Gaussian, and then the parameters of that Gaussian are drawn from other Gaussians, would it essentially just keeps inferring the parameters down through the, okay.
Yeah. And that's kind of the beauty of probabilistic programming languages, is that you can start with something very simple, but it's very easy to start saying, oh, maybe there's some hierarchical uncertainty. Maybe there are different kinds of people. So you can imagine, okay, now maybe there are, wimps and strongmen, and the mean strength is different for those two groups. You have to infer which group does this person belong to, and what's their strength, and what's that, etc.
Do they need to be generative models?
So the models are generative except for the conditions, and I didn't show you factor statements, but there are factors. So they're actually a combination of generative and undirected. Conditions are basically undirected components. Yeah. There's not as big a difference between generative and directed as you might think that there is. But they're generative, not discriminative, if that's the question.
Yeah, thank you.
I'm sorry if this is a little bit tangential, but I'm kind of curious on when they put these models on the strength of the players for the online games, how much did that improve the willingness of people to engage in those types of games?
I don't have so they tell me that this was useful, but other than that, I don't know. You'll have to go ask the Microsoft people. I would guess it's very useful because it's really frustrating if the games are too easy or too hard. Right?
Yeah, I've had that experience where years ago I tried to play some online game, and it's like everybody in there is like a professional player in Korea or something, and I'm just this casual guy, and I don't,
Yeah, exactly.
How hard is it to change your distribution from Gaussian to something else? I mean, most things, not hard?
Yeah. Maybe talk about it later, but it's pretty trivial. You can use a bunch of ones that we built in by building in a math library, or you can define your own pretty straightforwardly. But let me give you a sort of elaboration of this to get across the point that I really want to get across, which is that this simple set of stochastic functions that we defined, you can use it in lots of ways. It's generative, not in the technical sense, but generative in the sense of productive. You can use it to make many, many, many different inferences from different data. So imagine a scenario where we now have this kind of dorky sports commentator pop up and give you some side information. Oh, by the way, I happen to know that player LS was lazy in game 2. So the question is, first, can people use that information? It's not clear that people would actually use it to update their beliefs about strength. And second, how would we represent that for the model? So for the model, it's just going to look like this. It's exactly the same model that gives our basic knowledge, and it's almost the same inference, except instead of just saying that the condition is Bob and Mary beat Tom and Sue, we can add, oh, and Bob is lazy. Right? Because what's in the condition is just some computation that has to return a Boolean, it can be anything. It can be something that goes ahead and checks whether Bob was lazy, and etc. So we did that experiment as well with people, and again, the model predictions match the human data quite well. People, turns out, do incorporate this omniscient narrator information in the way that the model predicts. Okay, so that's a first kind of very simple case study of capturing some conceptually interesting knowledge about the world, in this case knowledge about skill in team games, that people have using a probabilistic program. Now from here I'm going to sort of move on to what I think of as more fun, rich knowledge. So I'm first going to think a little bit about social knowledge and social learning, and then we'll head towards language. And we'll see how much time I have. Okay, so here's another fun thought experiment. This is the one that I call Bob's Box. So imagine you have a friend, Bob, who has a favorite toy, which he brings to the office one day. And it's this box that has 2 buttons and a light on it. And at some point during the day, you see Bob press the 2 buttons and the light goes on. And now the question for you all, this is a thought experiment, is how does the box work? And here are your options. You could decide that only button A makes the light go on, that only button B makes the light go on, that actually either of the 2 buttons would have made the light go on, that you need both of the buttons to make the light go on, or that there's actually no relation between the buttons and the light and it was just a freak occurrence. Okay, so everybody choose your answer. How many think that button A alone does it? How about button B alone? How about A or B? Okay, and what about A and B? Yeah, I love this thought experiment. It's so reliable. So about a third, like, a small smattering of you said something else, but about a third of you said A or B, and about 2/3 of you said A and B. And if you ask people why would you say A and B, and I'll show you experimental evidence in a second that people do this, what they're going to tell you is that you're going to say A and B because, well, why else would Bob have bothered to press both buttons unless he had thought that he had to? They're going to talk about Bob and his beliefs and his goals and his knowledge. Okay, so the task for us is going to be capturing that inference based on knowledge about Bob and his beliefs and goals. First, I want to just show you the experimental evidence to convince you that what you did was very typical. So we did an experiment where we made up a bunch of these crazy stories, all of which had the exact same causal structure as Bob's Box. So you work at a plant nursery, and your coworker pours a yellow liquid and a blue liquid on some flowers that are almost dead, and then at the end of the day, they're growing again. What causes the flowers to grow? We give them the same options. Critically, we also, because we're psychologists, have a control condition, and in the control condition, all we vary is this middle paragraph, and we make it something where there's no person involved. So a small earthquake knocks over the blue liquid and the yellow liquid, and at the end of the day, the flowers are growing again. Okay, and we did this with 9 different stories. I'll just show you the data to start with. So in the social condition, people overall say A and B are needed, both causes are needed, and it's about twice the rate of the or. In the physical condition, that reverses, and there's sort of no statistically significant difference there. Okay, so that tells us that, yeah, what you guys did is very typical, however you were reasoning, but that it really depends on there being a person in the situation. Okay, so how are we going to model that? Well, first let me show you what it looks like if we don't include knowledge about people and how they choose their actions, what beliefs and goals they have. So this is a kind of standard causal learning model where we just say, look, there's some actions that we don't know where they come from, there's some events that happen as a result, and then there's the true causal structure that is sort of intermediate between the actions and the outcomes, the actions and the events. And then if we do Bayesian inference, we can use it to go backward, to go from actions, so we condition on actions and events and try to make a guess about the true causal structure. And here's a sketch of a model like that. It's a probabilistic program. This is not all the details. It says, okay, look, there's some causal structures for the world, and we uniformly draw one of them, so we don't have any a priori knowledge about which causal structure is right. There's some actions that Bob could have taken, and we uniformly draw one of those. We don't have any theory about where Bob's actions come from. And then the outcome is what happens if you just apply the world causal structure to those actions. And then we condition on what I told you, so that the action was pressing A and B, and the outcome was the light going on, and we see, okay, what's the causal structure? And this predicts very weak inferences. You might think that's bad, but actually this is sort of what Karl Popper or other kind of philosophers of science would have told you to do. You observed confounded evidence, you shouldn't draw a conclusion until you can deconfound that evidence. Right? So this standard causal learning model draws very weak evidence, very weak conclusions. It says, I don't know, there's some relation, but I'm not sure what it is. Okay, so here's what we want to add in order to capture the reasoning about Bob and his beliefs and goals. We want to add the idea that, hey, those actions actually come from somewhere, and where they come from is Bob making a decision based on what he believes or knows about the world and what he wants to have happen, say, make the light go on. And then what we're going to do is the same inference about causal structure, but given this additional piece to the model. Okay, how are we going to capture that? Well, what we have to do is write some kind of piece of probabilistic program that captures the idea of making a good or rational decision. So, this is one way to represent rational decision making as a probabilistic function. It's a function that takes in the causal structure of the world and a goal predicate that you apply to an outcome to see whether your goal is satisfied or not. And it simply says that to make a decision, you imagine an action a priori. You imagine what outcome will follow if you take that action, given the world causal structure. And then you assume that your goal is satisfied for that outcome. And you say, okay, what action did I take? So this is a kind of funny sort of optimistic reasoning where you say, okay, imagine an action such that my goal is satisfied. What action is it? It turns out that this is also equivalent to a standard Bayesian decision theory formulation of approximately optimal decision making. What's cool though, and notice that critically there's this infer in here, right? So what this decision making thing does is it models somebody making an inference of what action to take, assuming their goal is satisfied. But critically, we wrap it all up into a nice function so that we can stick it into the model that we were building before, the causal learning model. So it's going to look like this. The only change from before is, first of all, we have to make a guess about the goals. And I say here, we don't actually know what the goal is. It might be making the light go on, it may be just pressing the buttons. But critically, the actions, instead of being drawn uniformly from the possible actions now, the actions come from applying this model of decision making. So we say, look, actions come in a way that depends on the beliefs and the goals of the person doing the actions. And it turns out that now if we do the same inference about what the world causal structure is, we get a much stronger inference, which looks much like the one from the human data, which is that, oh, probably you need both of the buttons to make the light go on. And why? Well, because the model now is trying to explain Bob's actions. It says, he pressed both of the buttons. He must have thought that he needed to, assuming he wanted the light to go on. And also I snuck something in here, which is that Bob's belief about the world is the actual world. Bob is knowledgeable. And so if he believes he has to, then probably you have to. Okay? Cool. And just to make the point, here's the model, social plus causal model prediction, and here was the social condition human data that I showed you before. And so they look very, very similar to each other. Okay. So what I did there was I showed you how you can effectively take a simple model which does the wrong thing from some simple evidence and augment it in a way where you're not adding any observations, right? The data, the evidence is exactly the same, but instead you're adding prior knowledge, you're adding a theory about why people do the things they do. And then that influences the inferences that you draw in a pretty radical way in order to, in this case, capture this Bob's box scenario, this attribution of a causal structure. Okay, so the next thing I want to do is make this a little bit more interesting. So the key thing that allowed me to do the Bob's box model was that inference, the infer operator, is a first-class thing. I can nest an inference inside an inference, right? The decision-making function has infer inside of it, and I put that inside the overall inference. Well, once I can do that once, you think, maybe I can do that more. What happens if I do inference about inference about inference? Question.
If you encode dependencies between different variables and the data kind of shows you that that dependency doesn't really exist, do you run into problems? Or does the data just kind of let you?
So it depends entirely on what model, what probabilistic program you've written down.
Could you repeat the question, please?
Oh, yeah. So the question is, let's see if I can get this. So imagine you have a probabilistic program that specifies some dependency between two variables. And then you observe a whole bunch of evidence in your condition that has no dependency between those variables. And the question is, well, does that screw the thing up, or can it learn that there's no dependency? And the answer is it really depends what model you've written down. So this is a modeling language, not a specific model. So if I wrote down a model that says, look, I have A, and then from A I sample B in a way that depends on it, like, by God, there's a dependency, you're stuck with that. On the other hand, it's very easy to then say, I want to entertain the possibility that there is no relationship, so I'll put a little parameter, which is the strength of the relationship, and then I'll draw that parameter from some distribution. And now all of a sudden, when I condition on my evidence, I update beliefs about that parameter, and that then will allow me to capture that there's no relation. So I'll say it again because I think this is the important take-home, which it's a good question. Probabilistic programming is a system for describing models, and each model captures some knowledge about the world. Of course, there are many different models you can write down about the same situations and the same evidence. Right? So the model is as good as the kind of assumptions and knowledge that you build into it. And this, of course, is a truism. This is as true for, say, deep learning models as anything else, despite what some deep learning people want you to believe. Right? The specific architecture you write down controls everything about what you learn. Okay, so let's play with reasoning about reasoning about reasoning. So this is what's called a reference game. The philosopher David Lewis spent a lot of interesting time writing about these things. So there's two roles in this game. There's the speaker, and so if you're the speaker, I'd say, imagine you're talking to somebody and want to refer to the middle object. Would you say blue or circle? Those are your only two choices. How many people say blue? How many people say circle? Okay, most people say circle because blue is confusable. And then the listener is the other side of this. Imagine somebody uses the word blue to refer to one of these objects. Which object do you think they're talking about? How many people think it's the middle one? How many people think it's the one on the side? Okay. There's a little bit of disagreement, but most people think it's the one on the side. And the reasoning is probably something like, well, you just square and not the circle. And it's through exactly this kind of counterfactual reasoning. Well, if he had wanted to talk about the circle, he could have said circle instead of blue, and so probably he's talking about the square.
So it seems that we're given a few kind of candidate hypotheses, and then we pick the one with the higher likelihood. And do you adopt open world versus closed world assumption in the sense that, like, for example, maybe there's something else that we can see, and then maybe it's there.
Yeah, that's a great question. So let me address it for probabilistic programs in general, this model, and the experimental situation. So this model is closed world because the experiments are closed world. We force the subjects to choose one of these objects in front of them. Of course, in the real world, it's not that closed world. And so it's actually critical to me that probabilistic programs are open universe models, probabilistic models. So, I could equally well, so I didn't actually specify for you the prior over objects here, the reference prior over objects given the context. But I could, in this case, I'm going to just assume it's a simple multinomial, right? Some probability of each of the objects that's there. But I could equally well write a recursive function that says it might be the first object I see, it might be the second object, it might be the third object, but with some probability it's a new object that I haven't seen, and I can kind of keep go on doing that. So it's actually exactly the open universe property of probabilistic programs is exactly parallel to the potential non-halting in ordinary programs. And it's the fact that you can have executions of a finite program that are potentially unbounded that allows you to write down open universe models, which is important.
I think if I were in that situation where, you said, okay, the guy says blue, and I really need you to pick one of these objects that he's talking about, My preference would be to flip a coin. Have you ever had anybody do that?
Well, I don't know whether what they do is flip a coin or not, but what I do know is what answer they give, and then I can aggregate across subjects and see whether, well, are subjects 50-50, are they biased, or they, what are they? So let me show you the data, actually. In this situation, we can imagine what we would say a lot, but the data are the data, right? This is the
Right.
thing about having experimental data. I will make one point before we go on to the data, which is that I didn't tell you what the distribution over the context objects is. I had this reference prior thingy. That has to be measured because we don't have anywhere to say. And it's basically, this is like, okay, of this set of objects, which one are people most likely to think about or to talk about a priori? So we're going to do one experimental condition where we measure that, and then the other two experimental conditions will be the listener and speaker versions of this game. Okay, so the speaker game, you can't read this, which is fine, because it's exactly the same as the game that I had you play. We show them 3 objects with 2 binary features. We circle one of them and we say, okay, which word are you going to use, green or striped? We have some catch questions here to make sure they're paying attention. How many dots are there or something like that? Okay, the listener is, again, exactly the same as the listener game. We show them 3 objects. We say, imagine somebody uses the word dotted. Which one are they talking about? And critically, we also have what we call the prior condition, and this is a fun thing. We say, now imagine that someone is talking to you and uses a word you don't know to refer to one of the objects. Which object is it? So because you don't know the word, that doesn't give you any evidence, and all you can do is tell us which object you think people are likely to talk about a priori. So we take the results of this prior condition, we plug it into the appropriate spot in the model, and then we predict the speaker and listener conditions. And the data turn out pretty nicely. So first of all, to answer your question, one thing that could have happened, and that some linguists say would have happened, is that the data would all be at 0 and 1, or 0, 1, and 0.5, because people are just drawing deterministic conclusions or flipping a coin. Fortunately, that's not what happens. There's a lot of gradation in the data, so if people are flipping a coin, it's a biased coin that depends on the exact context. And the model is able to capture that variance quite nicely. So there's gradation in the data, and the model predicts that gradation, explains 80% of the variance in the data. And what's cool is that the model really is a simple model once you have the ability to write down this kind of nested inference structure, inference about inference about inference. Okay. Other questions? Okay, so the next 15 minutes, I'm going to talk faster and tell you about fewer of the details so that I can show you some kind of super cool things. So the first thing I'm going to say is that we can soup up that model of reference games to a much more complete model of language understanding without changing too much. You don't have to read this too much. I guess the slides will be online at some point. You can look at a bunch of papers we've written about this framework, which is called the Rational Speech Act framework. The critical thing is just that at the end, the literal listener grounds out not in the actual properties of objects, but in some meaning function, which is where your sort of syntax and semantics goes, the stuff that maps from a string of words into a function that says whether the utterance applies to the world or not. Leaving out some details, you can do that. I will say that if you like linguistic examples, you've probably seen the scalar implicature thing before. So if Gregor Mendel says some of the apples are red, the probability is good that some but not all of the apples are red. You can capture this very nicely in this this Rational Speech Act model. And I'm not going to show it to you, but if you go to webpeople.org, it's one of the preloaded examples that you can play with. So just go there and play with it if you're interested in that. Because instead what I want to do is show you something that I think starts to get at the, wow, I didn't think you could model that sort of modeling. So non-literal language is one of the most interesting parts of language and one of the hardest. So it's things like metaphor, there's Romeo and Juliet, and the one that I'm going to look at today is hyperbole. So indeed I mentioned that it took 1 million years to get the waiter to our table to order. So what that poster doesn't mean is that it actually took 1 million years, right? What they mean is that it took kind of long and they're really annoyed about it. Or here's some more examples, just for funness sake. I told you 1,000 times already. My phone is 100 years old. a latte at that hipster place cost $10. I left this one in my talk. I haven't taken it out because I like the fact that when I give this talk in New York or San Francisco, people don't think that's hyperbole. But in most of the country, people think that's hyperbole. Okay, so here's the puzzle of non-literal language. So understanding a sentence has to start in the conventional meaning of the words in that sentence. Otherwise, words don't mean anything. So it has to start with the literal meaning. But language is very often used in ways that are actually false under the literal meaning. And they're literally false in the literal sense of literally, not the conventional now sense of literally as figuratively, which is incredibly confusing. Another way of saying that is, why is it that exaggeration is not the same thing as lying? Right? So unfortunately for us, the little RSA model that I flashed on the screen just a second ago, in its ordinary plain form, isn't able to capture this sort of non-literal usage. It's able to do a lot of interesting things with strengthening meanings and shifting them around, but what it can't do is just throw out the literal meaning and move somewhere else and say, oh, actually the meaning is this other thing. So we wrestled with this a little bit, and then we realized that there are these two interacting changes that we can make to the model, which do something really interesting. So the first change is that we observe that non-literal interpretation is often used to convey information about opinion or the affective state of the speaker, not about the objective world. So one thing that we have to do is say, okay, the world that we're using in the model, the inference about the world part of this model, it has to be about a world that contains the objective state about the world and then the speaker's subjective opinion about the world. Okay, that's a really simple change to make in this model, and that alone turns out not to do anything useful. The other thing that we can do is say, hey, sometimes the speaker's goal is actually not telling you anything about the objective state at all. Their goal is purely telling you about their opinion, their feeling about this situation. Right? I waited a million years to get the waiter to our table. All that poster is trying to say was that it was an outrageously long amount of time that that they didn't appreciate. And so what we need to do is allow the pragmatic listener to reason about what the speaker's goal was in saying that utterance. So I like to call this the topic of conversation, reasoning about the topic of the conversation. Linguists would call it a question under discussion, T to G.
I would think there's one more important thing that would be missing there. And if you said that you waited a million years for a waiter, he's actually just expressing frustration. Does that mean he ever come out?
That's what I mean by the subjective state of the speaker, right? The affective state, irritation or something like this. And I'm going to, in this initial case, violently collapse all opinion to no opinion or some strong opinion. There's follow-up work that we've done that digs into that a little bit more, which is interesting. But okay, so just to give you a quick snapshot of what the model looks like, there's, relative to the previous model, there's really just a few small changes. The critical one is that we have to have an inference up here in this listener's inference. We have to infer this topic or question under discussion, which is then used down here in the speaker. And what we say is, look, the condition of the speaker is not that the listener is going to guess the true world. It's that whatever world the listener guesses, when you project it along the question under discussion, the topic, it's going to have the right value as if you project the actual world. So if you only care about the speaker's opinion, if you extract the opinion from the world that the listener imagines, it'll be the right one. Okay. And then the only other thing to say is that we extended the actual world to have the actual state and the affective state of the speaker both in there. There's some details when you can look in the paper. And then we run some preliminary experiments because we need some prior knowledge here. We need to know how expensive things actually are. The domain we're going to use is cost. So I paid $1 million for that electric kettle. So we first elicit priors over prices of things from a bunch of subjects. We then elicit the probability, there's some data, it doesn't matter, then we elicit the probability that somebody will think that an electric kettle is expensive given how much it actually costs. So this is the prior over affect or opinion. And then we can plug this into the model. There's some data. And what we're going to use it for is predicting this data. This is interpretation of number words. So the target data is things like this. Oh, Eric bought a new electric kettle, a friend asked him was it expensive, and Eric said it cost $10,000. And then what we ask subjects is, okay, so how much did the kettle actually cost? So if the subjects are interpreting this literally, then they'll put the $10,000 slider up at the top and everything else at the bottom. But they don't have to. They can interpret it sort of however they want, put the sliders wherever they want. Long story short, here's the data versus the model from this experiment. So the correlation is kind of ridiculously good for an experiment like this. We're explaining most of the data. But the cool thing about this is that so if you look at the orange dots here, those are the cases where the interpretation, the slider that people are putting high is much less than the uttered price. So this is a case of a hyperbolic interpretation. And the hyperbolic interpretations, it's not like they're all clustered down at the bottom. There's nice gradation to that, corresponding to whether an utterance is hyperbolic is quite different if that object is an electric kettle than a laptop, right? And the model is able to account for that. It incorporates the prior knowledge and does this inference about the goal in order to capture the hyperbole, or lack of hyperbole. Sometimes there are literal interpretations. Let's see, I've got about 5-ish minutes left. Is that true? Or should I wrap up? Or?
Yeah, 5 minutes is good.
Okay. So let me briefly show you one thing. I'll skip all the modeling stuff and just sort of tell you the results, which is fun. So here's another. So hyperbole is a big, and non-literal language in general is a big puzzle of language use. Here's another long-standing puzzle, the puzzle of vagueness. So tall is a funny word. A tall building is really different than a tall man, right? But the word is the same. There's some other signatures of this kind of vagueness. So there are borderline cases, maybe being generous to myself, of saying, if somebody says Noah is tall, you'll be like, I can't say that that's true or false. He's sort of borderline in between. And then there's this fun one called the Sorites paradox that goes like this. The Sears Tower is a tall building. Everybody agree with that?
Yeah.
Good. A building half a meter shorter than a tall building is tall. Everybody agree with that?
Yeah.
Yeah, so the two of you are being logical. If you ask a real person, they'll say, yeah, that's pretty good. And critically, you can make this 1 micrometer shorter than a tall building, and even engineers will probably say yes. Therefore, by mathematical induction, all buildings in Chicago are tall. Right? So even ordinary people, if you ask them, are all buildings in Chicago tall, they will say no. So the puzzle here, the psychological puzzle, is how are people reasoning about this information such that they're really happy with the first two statements here, but they're really unhappy with the last one, even though it seems like by mathematical induction, the last statement follows from the first two. That's the Sorites paradox. It goes back to ancient Greece. Sorites means heap, because the original version of this paradox was, if you have a heap of sand and you take a grain away, it's still a heap of sand. So when you have 1 grain left, it's still a heap. Yeah. Okay, so here's what we're going to do. We're going to elicit some priors. So we, again, use these prices of a bunch of categories of prior probability of prices for a bunch of different kinds of things. And then we're going to ask people both the concrete premise, so a watch that costs X dollars is expensive, agree or disagree, and the Sorites inductive premise, a sweater that costs $8 less than an expensive sweater is also expensive, agree or disagree. And then we can just compare that to the model, which I haven't told you all the details of. And the result is, bam, we can explain all of that data. I'll give you just the insight about what the model is doing, since I'm not showing you the details of the model. The basic idea here is that expensive is underspecified. The semantics, you can go look at the paper on this. Oh, well, no, you can't look at the paper. I can send you slides with a more detailed version of this. I just remember we haven't actually published this paper onto our website yet. I'll just get this. You can also use the same model to deal with generic language like you always have for okay, so let me take one step back and try to wrap up. So this is the cognitive computing enthusiastic club. What is the point about all of this for cognitive computing? And so the first question is, why did I spend so much time talking about humans, human judgments, and actual human data. It's because I think the cognitive and cognitive computing has to be rooted in the intelligent things that people actually do. And so the work that I do is very much inspired by looking at some interesting and puzzling behavior of people that seems, puzzling but smart in some way, and trying to see whether we can come up with a reasonable explanation, a reasonable but precise formal explanation. In all of these cases, what I did is I showed that using the modeling language that's provided by probabilistic programming, we can write down models that predict the behavior of people. So this is not directly testing probabilistic programming. That's just what Kuhn would have called a framework level hypothesis. It's a way of formulating hypotheses about what people know. But the critical thing is that it's a way of formulating those hypotheses that turns out to be able to capture at least some cases of rich common sense knowledge about teams and games and all sorts of good stuff like that. And as I showed you at the end, it kind of scales up. We can scale up that rich knowledge to knowledge about language, which then lets us build these interesting context-sensitive models of language understanding. So my thesis is that this is actually a critical step toward cognitive systems that actually represent and use knowledge the way that people do, right? So there's lots of different ways to represent knowledge, and there's a big, long-standing puzzle of which ways are going to be the most able to be useful, but also capture a rich structure in the world. I don't think I gave you it's not like this is the end of the story, but I gave you a couple of pieces of evidence that this is an approach that can capture interesting, rich structure. Okay, now a lot of you are from industry, and so you're sitting there wondering, yeah, but is this actually something you can, scale out and deploy in the world? And the answer is probably not today. It's already pretty good for rapid prototyping and sort of exploring different modeling assumptions against relatively small data. And the bottleneck is that we have to scale up the inference, the actual algorithms behind that infer keyword, to deal with much bigger model and data complexity. Now the good news is that we and so my group and a lot of other groups around the world have been working on that for the last 5 to 10 years. And a lot of rapid progress is being made, particularly the first 5 years when I worked on this were kind of slow and painful. But now a lot of people are working on it, and the progress seems to be really heating up. There's been a big DARPA program funding research on this, for instance, that has gotten a lot of people working on it. And I would say that I'm cautiously optimistic that these probabilistic programming languages are actually going to be useful at scale in the next couple of years. So this is maybe a reasonable time to start thinking about it, or at least keeping it on somebody's radar. And I'll just shamelessly plug 2 things that I'm involved with. So I already plugged the Web People programming language, which is the academic open source programming language that we are building in my lab for a lot of this stuff and playing around. Gamelon is a mostly stealth mode startup that I've been advising that is building, as they say, machine intelligence based on probabilistic programming tools. So if you go to gamelon.com, you'll see a beautiful but cryptic web page that at least gives you an opportunity to send an email to somebody if you're interested in that kind of thing. And that is the end, except for some links. So more on cognitive models, you can look at probmods.org, and more on probabilistic programming languages, you can look at dipl.org. And thanks to the people who give me money to do all of this stuff. And thanks to you.
I think we have time for a couple questions. If you guys have some questions for Noah.
Okay.
So there's 1,033,273 objects in the world that people could apply these fuzzy linguistic descriptors to. How well would you be able to generalize? If you're talking about, like, if you train it on knowing how fuzzy language applies to tall buildings, how well would it then be able to kind of say, well, I know in this domain that's fuzzy, and then this other thing that I've never heard of before might be fuzzy as well?
So So there's a half full, half empty answer to that. So the half full, some ongoing or kind of, maybe I call it the next generation research in my lab that I'm excited about is actually combining the kind of approach that I showed you with two other things. One is work from semantic parsing, where you sort of learn aspects of the meaning from usage data, from actual utterances. And then the other is using some deep learning stuff in order to make the inference that you have to do that more tractable. In principle, what that will allow you to do is learn meanings from usage. If we can get the inference working, I'm actually quite optimistic that that will generalize well, because both the pragmatic structure of the model and the compositional combinatorial structure of the semantics they kind of enforce generalization. So rather than just having to learn the meaning of each sentence in each context independently, they strongly tell you the relationship between meanings of different sentences that contain the same words and different sentences in different contexts. That's probably totally uninterpretable, but I can unpack it for you if you like. So I'd say, we don't know how to put in the learning thing yet, but it's something that we're working on, and I think it's pretty likely to work.
Do you try to duplicate your experiments using people from different cultures and different languages?
Yeah, good question. So I don't do cross-linguistic work. I have collaborators and colleagues who do. I don't, because I only speak English. I'm unfortunately an American. And so I just don't have intuitions. There is quite a bit of cross-linguistic work on scaling the adjectives, for one thing, hyperbole, a little bit less so, things like scalar implicature. And to summarize a very large body of work, I think the finding is that most of the principles of pragmatic interpretation seem to be common across languages, although the exact means that you have of interpreting vary. And I think it's kind of an open question how much cultural variation there is, and what would be the right way to capture it. Is it in the priors? Is it in the lexicon, the meanings of words, or somewhere else?
So is the framework limited to kind of like black box optimizers at this point?
You mean the actual inference?
Yeah.
No. So this is a different talk that I decided not to give about how the things actually work. So in web people, for instance, we have a bunch of different standard inference algorithm strategies. So we have enumeration, dynamic programming. We have markup chain Monte Carlo, sequential Monte Carlo, variational inference, some combinations of those things. The point is really that if you can cover a lot of different things, then you can try out different inference strategies and see what seems to be appropriate for your problem. So the variational ones are kind of black box optimization approaches. The markup chain Monte Carlo ones are not. They involve program introspection. They're pretty standard as these things go, but they're not optimization. Basically, they're Monte Carlo inference. There's of course a lot of details about how you can take these statistical algorithms and apply them. Because essentially what you're trying to do is generalize them to a state space which is specified by the executions of a program, the target program. It's sort of an interesting thing. Actually, if you look at DIPL.org, Design and Implementation of Probabilistic Programming Languages, that's what that stands for. That's sort of a tutorial where we walk through several different algorithms. So we walk through enumeration, MCMC, and sequential Monte Carlo. Kind of insight into how you would implement a thing like this. Yeah.
So this is a very, excuse my voice, very entry-level question. So I have no background in programming. I have experience within economics and statistics, specifically econometrics, but I'm absolutely interested in probabilistic programming and models of cognition. What would be it's like one single serving size advice you could give on where I should start to begin learning everything?
That's
Could you repeat the question, please?
yeah, sorry. So the question is, for somebody with not a programming background, but more of an econometrics background, where can you start learning about this kind of thing? So I'll just go ahead and plug my little web book that I used for teaching my class. So probmonths.org is basically a book about probabilistic modeling of cognition. It does it using, actually not Web People, but Church, the predecessor language to Web People. And the point is that I've actually found that in teaching this stuff, it's much easier to get a handle on complex probabilistic models by thinking about them in terms of simple programs than thinking about them in terms of the probability math. And I think that's true even if you haven't done any programming, because as you might have noticed, the actual programs are pretty simple here, because even a simple program ends up representing a pretty complicated probabilistic model. Okay, having shamelessly plugged my own thing, I will say there are many other sources for learning about cognitive modeling more generally. There's like, I think one of these handbook kind of things, the Handbook of Cognitive Modeling, which your mileage may vary. Some of the articles in there are great, some of them are not so great. Of course, coming from economics, there's a whole parallel literature on behavioral economics that's very relevant.
Yeah.
So if you want to model maybe with a large number of variables, how do you, who are your techniques for handling the exponential growth of
Yeah. So the question there was, so if you want to handle a lot of latent variables in a model like this, what do you do? And so it depends on how many is a lot. So up to a couple of thousand latent variables using Monte Carlo techniques seems to work pretty well. Particularly if you're using continuous latent variables and using Hamiltonian Monte Carlo, which is a gradient-based Monte Carlo, seems to work well. And that's what we tend to do up to like, maybe 5,000 or 10,000 variables. If you want to go above that, then you end up needing to use more radical approximations. Any other questions? Great, thank you all.